A little, like,
I know Peter's here. So I don't-
I think, should we wait for Peter to get back in the room, or he just put his?
clearly, he introduced himself, you said hi. I reminded him when I
Okay, I
embarrassed
think
myself.
maybe we should just start because it'll eat into Scott's time.
So hi everybody and welcome. It's my pleasure to introduce Dr. Scott Hughes. Dr. Hughes is joining us from just down the street at MIT, where he's a professor in the physics department and also at the Kepler Institute. He's written extensively on gravitational waves, and today he's going to be talking to us about the future of gravitational wave research, a part of our two-part series on gravitational waves. So his topic is titled "Where Do We Go From Now? Thoughts on the Road Ahead for Gravitational Waves."
All right, thank you. So it's great making the long trek to get here and to deliver this talk. I kind of want to preface this by saying this is very much my view of where the field is going. If you poll a bunch of others in the field, they won't quite agree necessarily on some of the details. I hope they agree kind of on the big picture, but this is coming from the viewpoint of someone who's a theorist who thinks in particular about how to model the kind of sources that we are measuring and what we want to use those models for. And I think that the way the field has evolved over the past couple of years, it sort of sharpened my thoughts on what that would be. And so this, I'm not going to deny it. This is actually a great opportunity to get some things down. They work on some grant proposals in parallel. So it worked out kind of nicely for me to organize some of these thoughts. And I want to begin this by introducing, sort of setting up a little bit of what I could call a, all right, that's not working. All right, let's use that. I think, yeah, I think the issue is that Zoom might have grabbed my presenter. So I want to talk a little bit about what I would call the fairly recent past. This sort of goes back to when I was in graduate school. So I started my PhD studies in 1993. And not too long before then, LIGO had been essentially approved for construction, and people were beginning to think about what it could be done. And when you looked at the literature, what people expected LIGO to measure, it was all about binary neutron stars. Neutron star was what everyone was talking about. And there were good reasons for that. We had observed binary neutron stars. They were a source that we knew exists. They were a source for which, as a theorist, we were confident in our ability to model the waveforms that would be necessary to measure these things. And thanks to the work of quite a few people, including Professor Narayan here in the front row, we had some confidence in how often these events would actually occur. So when you put all those things together, this was at least, there were knowns here that gave us confidence. This was something that we should look at. Now, as part of what turned into a big chunk of my thesis work, my PhD supervisor, Kip Thorne, suggested we start thinking a little bit about what the sources would look, what the measurement space would look like for binary black holes. And so setting aside all of the astronomy and all the astrophysics, we just thought about this from sort of a physics point of view. What do the waveforms look like? And how do the waveforms appear? What are their characteristics relative to the sensitivity of these detectors? And this, which is taken from a figure one from a paper that I wrote with Anna Flanagan, sort of showed that if we made, bear in mind, numerical relativity had not modeled two black holes merging. They were at least 10 years away from being able to do that at that point. So we just did some physics-based estimates as to what the power in the waveform looked like once analytic techniques began to break down. And what we were able to show was that the LIGO sensitivity and the Virgo sensitivity, basically the sensitivities of all the proposed ground-based instruments, was such that they were very well aligned with binary black holes, but mostly for a piece of the waveform where the analytic techniques that were then being used would not work well. We sort of took this as an exhortation to the numerical relativity community, get things working, because we are going to need those waveforms. And indeed, we, at the end of this, if we were able to get those waveforms, we actually stated that binary black holes might very well be the first detected sources by the LIGO Virgo instruments. And in fact, it goes to our paper, we call out a mass range of about 60 solar masses, particularly interesting, which turned out to be pretty entertaining in retrospect. But when we put this out, it kind of, I think the numerical relativists listened to us, but a lot of our astronomer friends basically said, yeah, you're barking up the wrong tree. And I was actually at a workshop in Paris in which my colleague Anna Flanagan presented our paper. And he was immediately followed by a paper that said, that's great, but you won't actually get any binary black hole mergers. And the reason for this was that, at least from the standpoint of thinking about those that formed from field binary stars, They would, due to mass losses and angular momentum losses in the late stage of stellar evolutions, the remnant black holes would be so widely separated that they, if you read this paper by Lev Jungelson and Simon Portuguese Art, all of the binary black holes are so widely separated that it would take many hundreds of Hubble times for them to merge into gravitational radiation. Something else would have to cause that to happen. Didn't rule out, of course, them forming via dynamical mechanisms, and there are some interesting things there, but this, we put it this way, when you're a fifth-year graduate student and you're starting to put out your first postdoc applications, and you give a big, your colleague gives a big talk on a big chunk of your thesis, and it's followed immediately by a bunch of people saying, yeah, take that talk and multiply it by 0. Let's just say that I'm glad Paris has a lot of wine bars, because we needed them that night. I will comment that not everyone was too worried about that, and I love the fact that as we were working on this paper, Kip thought that our prediction was a little wishy-washy and told us, you will regret not phrasing this prediction more strongly when LIGO is regularly measuring merging black holes in about 5 years. Bear in mind, he said that in 1996.
So, but I don't understand the objection, stellar wind objection. What are they saying?
They're basically saying that if your binary black holes come from 2 main sequence stars,
Right.
those stars have to evolve to form black holes. In the course of doing that, they're going to shed a lot of mass. They're going to lose a lot of angular momentum. And when you use the models, in particular the models for how stellar winds carried mass and angular momentum away from systems in binary evolution at that time, you tended to be left with binaries that were separated so widely that they just, gravitate. If you say the only thing that's going to evolve them now is gravitational radiator back reaction, it would take 100 or 1,000 times the age of the universe to bring them together.
So they lose angular momentum in their mutual orbit or in their spin?
In their mutual orbit. Yeah, so that was what was driving it. You're leaving them so widely separated that they would never actually merge. What's interesting is that a couple of years before this, before the sort of wisdom instantly changed, the fashion began changing. Monica can probably tell you a lot more about this. This is very much related to the kind of things that she thinks about. But one of the things that already people beginning to appreciate is that some of those calculations of how stellar winds would carry away mass and angular momentum, they were based, among other things, on an idea of what the typical opacity of the material would be, which was probably not calibrated to the right kinds of stars. And so more modern calculations were actually saying, you know what, through normal stellar evolution, maybe you're not going to get those. And we began seeing more and more calculations that were doing this, that were producing things that led to what we actually observed on the morning of September 14th, 2015.
Okay, can I ask some questions?
Yeah.
I'm just trying to get this square in my mind. If you lose angular momentum, you go closer together, don't you?
Well, you're also losing mass, right? And so it's a combination of, I think mass is probably the most important thing,
Okay,
actually. Yeah,
because
because if you fix angular momentum, but you leave the mass and you make the masses get smaller, then you're going to need to go out.
That I got, but if you lose angular momentum.
That's true. Yeah.
You definitely go closer
That's
together.
right. That's right. So it was I should rethink the way I explained this. I think it was mostly mass losses that were the important thing in this.
Okay.
Anyhow, so for the purposes of this talk, one of the things that was really exciting when this happened is, just boom, you sort of got it there. And from a standpoint of a gravity theorist, you instantly saw that the global waveform that was being measured required consistency with the predictions of general relativity. Not just like weak field general relativity, but really doing strong field dynamical general relativity, the full space-time dynamics were needed to explain these data. And they just keep happening. So this is already an out-of-date slide, but we've now seen well over 100 of these that have been found and analyzed. Okay, I don't know what the status is on writing up the next catalog of discoveries, but this is based on various plots I've seen. You're going to increase this 100, is going to become several hundred before too long. And the band has recently been getting wider. So something which I have to highlight somewhat because the corresponding author on this paper is a former graduate student of mine. The long-term monitoring of many radio pulsars, it was long expected that it would be sensitive to a hum from stochastic waves from many sources. Basic idea here being that you can think of an isolated pulsar as just a very regular clock, and a gravitational wave is going to come along and disturb this regularity. And so you set up an experiment where you just monitor many hundreds of these clocks, and the pattern of disturbance will have a particular correlation depending on how widely separated pairs of pulsars are on the sky. And what was announced in this paper that was just put out about, at this point, it's almost a year and a half ago, was the discovery of the so-called Hellings-and-Downs curve. So this particular shape is what you expect if your pulsars are being disturbed due to a quadrupole radiation pattern.
Those from stellar or supermassive black hole mergers?
Probably supermassive black hole mergers, almost certainly. That's a very good point, because actually, let me do the next slide that I have here. So what with the most plausible explanation for this signal is indeed exactly as you say, superposition of gravitational waves from many massive binary black holes. Are you an author on this paper?
Yes.
You are, okay, yeah. I love this paper, and I can now say this because I was the referee. And so it was a good chance to actually read it. And so one of the things which was particularly cool about it was, so to answer what you were just asking about, Peter, so on this, they have gravitational wave frequency in inverse years. So take the inverse of that, they should tell you the periods. So this ranges from periods of about a year up to 10 years. So this is indicating very massive, very wide separated things. And one of the things that's already particularly cool is that you're seeing this purple line is what you would get if this population is evolving only under the influence of gravitational waves. There seems to be a bit of a bend in it, which requires some mechanism to actually be bringing them together a little bit faster than just gravitational waves alone. So we're starting to see some astrophysics of the formation and evolution of these binaries already showing up in this very first data set. So where do we go now? I'm not going to talk about the pulsar timing, except I have a parable about it to discuss in just a moment. But for the most part, I think what is driving a lot of our thinking are the new instruments that are coming online. And what I would say is that we've kind of gone through this gold rush. And we're becoming the gravitational wave field is becoming a very data-driven field. The detectors are evolving. They're going to be able to sort of hear more of each signal. And because of this, we're going to need to develop models that can keep up with what the detectors provide for us. I am personally most worried about understanding systematic effects as we begin developing these models. And I'll talk a little bit about some of the ways in which I'm concerned about this throughout this talk. So as you look at the landscape of future instruments, here's sort of a LIGO right now is actually a little bit below this. It's somewhere in here. And here's a sort of smorgasbord of various ground-based instruments that are under development. Here is a space-based observatory, the Laser Informative Space Antenna, rapidly under development as well. And sort of the thing which drives thinking about what we're going to be learning from these future instruments is you're improving strain sensitivity. So the mean H that you're typically measuring is getting quieter and quieter. And so you're able to pick up more signals and really zoom in on them with more detail. The bandwidth is getting wider, in particular, as we look at these ground-based instruments, we see that the lower frequency tends to get pushed down more. What that means is that signals enter your band earlier and you pick up more and more signals. There's a lot more leverage to, I'm sorry, I'm actually doing band to begin with, my apologies. So particularly thinking about the space-based instruments, they go to a much lower frequency, and so they're sensitive to a different part of the gravitational wave spectrum. Now bandwidth, you have signals that are in band for longer, and you're able to pick up much more detail of the wave's evolution and its nature. So there's more waveform cycles, you get high precision on the gravitational wave properties.
What's NEMO?
NEMO was a proposed instrument put forward by colleagues. There's a group in Australia that doesn't really have funding to develop a very large-scale instrument, but they have been pushing ideas for things. And so this is something that was meant to go, the N stands for neutron star. I think it's like neutron star extreme matter observatory or something like that. It's kind of like a gravitational wave nicer type of idea. And so their idea was to try to do something that sacrificed bands to try to just do as much as possible here at high frequencies where you might want to try to catch signals from the end state of two neutron stars coming together. It was really just a proposal. I like this graphic. The one thing I don't like about it is I always have to explain that because it looks like it's not moving forward. But
Well, the sensitivity curve looks a little odd compared
yeah,
to
yeah,
others,
exactly.
right?
Very much so. Very much
Actually,
so.
I'll ask another obvious question. The future Cosmic Explorer Einstein telescope, they're able to go all the way down to 10 hertz.
That's what
What's
they're
the,
being
what's the
designed to
big
do.
breakthrough there?
Getting down to 10 hertz is actually not terribly hard. You just need to have really good seismic isolation. Okay, and if you look at what LIGO is doing now, it's essentially if you just take what they're already doing and just do it better, you kind of expect to go down there. Okay, and that basically doing it better means making your the suspension stack a little bit higher more than anything, right? So these are basically on pendula. The frequency of a pendulum is square root G over L. Make L larger, you go down to higher. You can go down to lower frequencies. It's actually going below that that's a challenge. And what sets the sensitivity, once you start going below that, you eventually hit a wall that you will never get past if you make a Earth-based detector, which is that the ground is vibrating. Even if you can isolate yourself from those ground vibrations, those vibrations gravitationally couple to the test masses because they stretch and squeeze the Earth a little bit. And so actually one of the chapters of my thesis was actually looking at what the ultimate limit was due to gravitational coupling to seismic noise. And eventually, probably, there was a paper I wrote with Kip Thorne, we could probably get down to about 6 or 7 hertz without too much trouble. Down to 5 is a little bit of work. Going below about 3 is pretty much impossible. So that ends up being the thing that ultimately sets that.
Can I also ask a question about the
Yeah.
noise?
Yeah,
So what drives these peaks in the sensitivity curves?
these little spikes.
Yeah, there's a lot in LIGO.
Yeah, and also up in LIGO. So every one of them corresponds to some specific mechanical or electromechanical feature of what is used to actually build the instrument. So I'll point out here in LIGO, if you count where, sorry, my email is still on apparently. If you look at what this is at, this is 60 hertz. In North America, thou shalt never escape 60 hertz. The equivalent plot for Virgo has a 50 hertz line. And there's another one that's at 180 hertz. And the cause of that is that one here. The cause of that is that the laser that drives this thing actually has a three-phase power driving system. And so it's 60 hertz coming in 3 times, essentially. Various other ones have to do with aspects of the suspension system. What can be, so those are, you would love to get rid of them if you could, but you're never going to be able to entirely, but they're very, very narrow. And so they're as it turns out, some interesting pulsars lay really close to them, and that is just, what can you do? Nothing you can do about it. But for the signals that sweep through bands, you just lose a little bit of power. It's not the end of the world.
Thank you.
So anyhow, where do we go now? So this sort of sets what's going on with the experiments. I want to turn now to my own expertise, which is thinking a little bit more about the theory. And to frame this, I like to quote an old philosopher and poet who was once involved in aspects of the American governance. Some of you may remember good old Donald Rumsfeld. And he once said in a press conference when asked about a particular issue, as we know, there are no knowns. There are things we know we know. We also know there are known unknowns. That is to say, we know there are some things we do not know. But there are also unknown unknowns, the ones we don't know, we don't know. He actually delivered this statement more or less with the cadence that I just said. He really was, anyhow, there's a lot we could say here, but it's not the right place and I'm not the right level of inebriation, so it's let us stay here.
Most cited quotation.
Yeah.
By the scientists.
But the reason I bring this up is that a lot of what drove many of us to sort of get interested in this field is because of the promise of the unknown unknowns. We wanted to think about what lies beyond general relativity. What is it that we can learn about gravity from what we are learning? And I think personally, what I have learned is we're not going anywhere near here until we deal with various known unknowns. There are so many things that come in and make this problem difficult. So many systematics that we kind of know are going to be there, but we don't understand their detailed nature, that these are always going to stand in our way first. So what have we learned so far? So the first point I would say is general relativity just works. It is turning into the standard model for this field in the sense that everyone's really excited about what's going to happen next, but we're never finding a crack. We have not yet to find a crack in order to get down to there. We have discovered that the kind of things that LIGO and Virgo measure come from a broad range of masses and mass ratios. We have clear evidence that spins are non-zero. They're sort of broad posterior distributions, but they tend to be peaked away from zero. The orientations are typically not that well constrained, but nonetheless, we sort of imagine as we get a broader band in particular, and we can see more oscillations, that will change. So these are now being used to constrain possible progenitors, learn about the populations of massive stars that form from these binaries. This is a wonderful tool for doing these kinds of analyses. There's a lot, though, that we kind of expect goes into some of the known unknowns that we have not seen yet. Okay, so we expect at some point, we're probably going to be seeing orbital eccentricity. We definitely see this in all inspiraling binary pulsar systems. But so far, all gravitational events appear to be consistent with zero eccentricity. Okay, there's some claims that one event might be due to an eccentric merger, but it should be noted, this event has roughly 4 oscillations that have actually been measured. So there are more papers published on that model than are wiggles in its waveform. Spins strongly misaligned with the orbit geometry has not been ruled out, but cannot be definitively established. And this is particularly interesting because it points to the mechanism by which these things have been would have formed. This already may be evolving at this point, and Monica can feel free to correct me if there are some updates here that I should be citing. Indeed, this event has characteristics in the late waveform that are consistent with it being a binary that was highly misaligned prior to the final merger. I'm going to talk a little bit about a phenomenon known as tidal heating. This is something that I think is a particularly interesting sort of phenomenon that is related to an aspect of gravity theory that I think will be very interesting in future measurements. It should, at some sense, be present already in what we are seeing, but it's very hard to measure. It boils down to a transfer of angular momentum between the spins in the orbit. And you should be beginning to see at some point things that are interacting with their environment. And I'll clarify what I mean by that in a little bit. So these all exist. They all be modeled precisely to avoid systematic confusion, both with each other and with other effects. And I think this is going to be particularly important if your goal is to try to understand what might these events teach you about the nature of gravity. And this is very much motivating a lot of my own thinking, because if you want to claim some subtle effect that is not consistent with Einstein's general relativity, you have to make sure you understand all the little bits of schmutz that are completely consistent with vanilla general relativity.
Is there a conclusive measurement of the spin?
There, I would say that there are, yeah. I mean, so the final ring down signal that you get when the final spins of the systems, absolutely. For the spins of the constituents that go into there, what I would say, as I worded on the previous slide, the error bars are large, but when you construct posteriors for what the distribution looks like, they all tend to be peaked away from zero. So,
Is there a degeneracy in the distribution of spin?
yes, well, there's a degeneracy in the waveform models, and that certain combinations of spin end up being certain aspects of them are degenerate with certain combinations of masses. Okay, that's part of what makes this difficult to measure. Okay, and it's one of the reasons why what you really would like is more bandwidth, so that you're measuring the way you break those degeneracies is by having a lot of waveform cycles where the effects separate from one another cleanly. And that's what makes these sort of more
Scott, you're
difficult.
now back to stellar binary black holes.
Yeah, I'm back.
Exclusively.
Right now, I'm focusing exclusively on the things that have been measured, the data that we have seen over the past 10 years.
What is the range of spins of the final?
They are clustered around about 0.7. And this is sort of the reason for that is there's some distribution, but if you have two black holes that merge with one another, almost independent of what spins go into them, the remnant has a spin close to 0.7 if the two black holes are of roughly comparable masses.
But is it a selection effect of the kind of thing?
I don't think that's a selection effect. There could be selection effects in determining what some of the spins that we can measure going into these things are. You certainly, probably not with what LIGO is currently measuring, but with some future measurements, very likely.
I was wondering what the status of the NR waveforms modeling eccentric binaries. Are there good waveform models for highly eccentric?
We come back to that in just a moment because that's a great question, and it comes up sort of naturally in some other stuff that I'm going to discuss in a few minutes. All right, so there's a parable that I like to discuss here, which is actually a result that was really cool and kind of funny. So when Nanograv's most recent discovery was from their 15-year data set, at the time of the 11-year data set, focus for a moment just on these lighter dashed lines. What this is after doing a complete fit of the data, they had a residual, a tiny residual in their data that was in these units 10 to the minus 15. Notice that the dashed lines here are peaked at around 10 to the minus 15. That is comparable to what they're expecting for a gravitational wave background, a little on the high end, but not too far off. And so people were like, are we already seeing it? This looked very, very exciting. Notice this paper I'm quoting here is published in 2018. When they looked carefully at it, though, the angular correlations don't actually follow the Hellings and Downs curve. It was not consistent with a quadrupole. When you dug in, there's a lot of noise, but it looked a lot more like a dipolar distribution. What could give a dipolar background? Well, in gravity, having the wrong dipole corresponds to having the wrong center of mass. Okay, and so bear in mind that when you make these measurements, now this is an 11-year data set. So the Earth went around the sun 11 times during all this. Other planets were perturbing the motion of the Earth, the barycenter of the solar system, quite a bit on some of those measurements. And it turned out that the ephemeris that they were using, the model for the solar system, was off. Okay, and so what they did, what happens, what's going on with these solid curves is they decided to let certain parameters that determine the barycenter float and determine it from the data. And they ended up finding that they needed to adjust the orbits of Jupiter, Uranus, and Neptune, mostly Jupiter. When they did that, the strong evidence for a background went away. And indeed, what they learned was that the original fit, the location of the solar system's barycenter was off by 100 meters. Okay, so the barycenter of the solar system, the center of mass of the Sun, Jupiter, Saturn, Neptune, Uranus, Earth, off by 100 meters. And that nearly led to an assumption that you would measure this very, very subtle effect. So I consider this to be a very interesting parable because it just shows how subtle some of the effects are that we tend to worry about. Nowadays, they actually use, there's a new ephemeris that is based on Jupiter's orbit in particular. It's been mapped out much more precisely with the Juno spacecraft. And when they use that, this effect goes away. And that was a key part of how they were able to get the discovery in the 15-year data set that I presented earlier.
That's pretty remarkable, 100 meters.
So
Like that,
when I talked
that's
with Mara
insane
McLaughlin
precision.
about this, she originally was like, describe this as improving our knowledge of the solar system. And she was actually a little bummed when Juno came along, like literally weeks later, and they had a better number, but it was cool while it lasted. You know, for about 4 weeks, they had the best measurement of the solar system of anyone. But you're absolutely right. How did they get that? By measuring stars that were thousands of light years away using radio telescopes. That's pretty cool. All right, so kind of getting
Stars or quasars?
stars. These were pulsars that were being used for this. So the reason is that they needed clocks, not so much like an inertial reference frame, but they wanted a time standard. So a major source of our challenge, what goes into when we're trying to model binaries and why I'm concerned about things like systematics, is I like to say general relativity doesn't actually have a two-body problem. It has a one space-time problem. Okay, so if we start with the space-time that has two well-separated black holes, Einstein's field equations tell us how to evolve it forward in time, and we can determine the system's dynamics and the gravitational waves it produces. But you have to determine things like what the masses of those black holes are, what their spins are from that space-time. And it turns out this cannot be done unambiguously. Work by Kip Thorne and Jim Hartle sort of laid this out at this point, so over 40 years ago. And it's not that hard to understand what's going on with this. So a black hole, strictly speaking, doesn't have a surface. It's just a region of space-time. We impose a surface to it by describing, we look for the place where events are sort of causally separated from one another, but there's no local measurement that tells you that you are there. From the space-time perspective, it's all very, very smooth. So if I have a particular space-time, there's a set of mathematical operations known as the Komar integrals, which are sort of an integral. You take a space-time, you make a two surface that contains some region, and this two surface, you can integrate over this, and it'll tell you things like the mass and angular momentum that's contained within that surface. If you have a symmetric and a stationary space-time, this gives an unambiguous integral that defines the mass and the spin of a black hole. But if you have two bodies, it's unambiguous, excuse me, it's completely ambiguous where you put the surface. And you're going to get a different mass if your surface is here versus if it's here. Both of them, if you just think of the event horizon as defining the surface, they both only contain one event horizon, but a wider surface sort of tastes more of the curvature of that other black hole. What this means is that when you're doing calculations like this, there is a built-in ambiguity in what you can actually define the mass and the spin of individual binary members to be. And when you ask yourselves, if you ask how well, bearing in mind this ambiguity, can I actually do this? It turns out that there is an uncertainty of about 0.1% on the masses and spins, which are comparable to the measurement goals of future detectors. The reason why this is important, this is partially related to the question you asked me a moment ago, is that even defining what some of these notions mean you can make this unambiguous by making these things initially infinitely far away from one another. Then this sort of curvature between them is negligible, and so you can make these notions unambiguous in that case. That's not how you do a simulation. That's not how numerical relativity works.
Oh, but couldn't you define the region to encompass both event horizons? There's a unique way to do that.
You can do that. That's right. That's right. It's still going to be somewhat ambiguous because you need to have your surface sort of be far away, but then what you get is just the mass and spin of the total system, okay? You're not calling out the individuals, right? So if I tell you that the mass of the space-time is 100 solar masses, you want to know, well, what's the mass of M1, what's the mass of M2? I was like, well, with this surface, it's 60-40. With this surface, it's 59-41, you know, and you know, that's kind of the issue. And so there's a built-in ambiguity there.
I have a follow-up question on this.
Yeah.
So you would use something like the Hawking mass on the horizon itself for each of them. That would give you I don't know about the angular momentum, but that would give you a mass measurement at least, right?
It would, but you do not, so if you have a dynamical space-time, where's the event horizon? Okay, that's one of the issues, is that to know the event horizon, you have to know the entire future history of the space-time. There are other notions of horizon that are quasi-local, and people define things based on them. I think there's some really cool stuff, but you always end up finding a little bit of ambiguity when you go into these things. So I'm going to focus for the next, my remaining 25 minutes or so on work that I've been doing, and a few ways I'm trying to understand this question using the extreme mass ratio limit. So this is an astrophysical system where you have a binary that is basically consists of a stellar mass compact object orbiting a massive black hole. We expect to find these in galaxy centers. What's nice about this is the binary's properties are dominated by the properties of the larger object. You can model what's going on with the smaller objects perturbatively. This allows us to do things very precisely. Many of these ambiguities, they scale with the mass of the secondary, and so they become negligible as you make the secondary smaller. They are also targets for LISA measurements. And one thing which I'm going to talk a little bit, and it's just sort of changed my thinking a little bit recently about what are the important questions in this, is that we may already be seeing some of these sources. So there's been a lot of work recently. My colleague Aaron Kara at MIT has been doing a lot related to this, indicating that at least some of these events that are known as quasi-periodic eruptions are likely to be related to having an extreme mass ratio system interacting with an accretion flow. And I'll show you some results for this. So from the standpoint of a relativity theorist, this is a really clean system, right? So you have a body that's orbiting a black hole. I know how to calculate the properties of orbits of black holes. One sort of way that's kind of cool to see what's going on here is that when you're deep in the strong field of a black hole, there are 3 orbital frequencies. Very wide separation. This is just Kepler's law. But as you move into the strong field, Kepler's, the sort of line corresponding to Kepler's law, splits into 3 frequencies that are related to radial oscillations, how long it takes to go from periapsis to apoapsis and back, polar oscillations, how it moves in the angular direction, and then axial motion as it sort of whirls around the symmetry axis. And a lot of what we observe boils down to beating between these different frequencies. So periastron precession is nothing more than a beating between the phi and the r frequency. So what I'm showing you here is a body moving on an orbit of a rotating black hole. It's a little bit inclined. My student who made this is now actually the CEO of a tech company, so he's not willing to update his graphics. But if you ignore the sort of wobbling of the plane here, you can kind of see that this is essentially the same basic physics as the perihelion precession of Mercury, okay? But dialed up by a factor of about 1,000.
What is omega phi and omega r again?
So omega phi is the frequency corresponding to the body going around the symmetry axis of the black hole. Omega r is related to the period, 2 pi divided by the period of the time it takes to go from apoapsis to periapsis and back if it's an eccentric orbit. In Newton's gravity, these frequencies are the same, and so you always get closed ellipses. In relativity, they are not the same. That's what leads to the perihelion precession of Mercury. And for a black hole, sort of, as I like to say, perihelion precession on steroids.
This is just geodesics?
This
or-
is just geodesics at this
Okay,
point.
not mass ratio correct.
That's right. That's right. And so, as you said, as you forthrightly brought up here, if I have a body that's like this and I include those mass ratio corrections, it changes the orbits. Among other things, they become gravitational wave emitters. And so you end up with a body that spirals through a sequence of orbits like this. So this is an example of a little simulation my former student Steve Drasko made years ago that everyone still uses, showing what this sort of looks like as it spirals through, in this case, about 100,000 orbits. So, we kind of expect measurement errors to scale as inversely with the number of orbits that are executed, along with inversely with the signal noise ratio, which sort of suggests that these should be tools for making very precise measurements of black hole properties. Okay, but coming back to my theme, we do need to start worrying about how we model these and what systematic effects could get in the way. One nice thing about one of the reasons why I like to work on this is that a lot of the challenges in numerical relativity, we have different challenges. So we can model these binaries perturbatively. So I'm going to treat the space-time as the Kerr metric, which describes a rotating black hole, plus a series of perturbations. The perturbations arise from that orbiting body. I can compute those corrections order by order in the system's mass ratio. And what you basically find is that the equation of motion, exactly your question, if this were 0, it would be a geodesic of that background space-time. We actually get a correction that is related to these H's that I've written down here. That's what we use to model these things. And it's worth emphasizing that this is actually the limit of the general problem in general relativity. So to the question you asked me about eccentricity, one of the things people are actively working on right now, even defining eccentricity unambiguously is challenging numerical calculation. Making sure that what you're seeing is actually a physical oscillation and not some weird coordinate effect is one of the challenges. A little more unambiguous in this thing. And so a lot of people are working on making maps between these things and trying to understand it as some finite mass ratio. So as I began working on this, I always would advertise this as, this is the spherical cow of general relativity. This is the case that we really want to spend our time thinking about. One of the things that I'll give you an example now of some of the things people have been thinking about what we can do with them and why, a little later in the talk, why I'm a little less optimistic about these days. So if we have a body moving in Newtonian gravity, we know that its motion, which depends upon the gravitational potential, is seated by the distribution of mass in that object. So I'm showing you here a gravity model that is made by orbits using a spacecraft called GRACE, the gravitation, something, or I forget what the GRA is, but CE is climate experiment. So this is actually a set of satellites that orbit the Earth to very precisely model the distribution of mass in the Earth. And so what they've done is you measure this phi through these orbits, you impose Poisson's equation, and you map out this multipolar distribution of how mass is distributed through our Earth. My
So
talk
these
is
are
not
like
about gravity.
Little columns that go down from the center of the Earth to the surface of the Earth and how much, what it's made.
That's a way to think about it. That's a really good way to think about it. Yeah, yeah. I'll make 2 comments about this. So one is that the CE, they can watch the way that the distribution of water changes seasonally over the course of things, and they have seen quite strong evidence for the loss of mass at Greenland as the ice caps have melted there. Another thing, which is both sad and fascinating, is that they saw the change in the Earth's potential at, I think I saw a talk on this, at about the 25 sigma level when the massive earthquake occurred in the South Pacific, over around Indonesia in 2005, the one that led to the tsunami that killed so many people. So that actually showed up in this data. From one orbit to the next, they saw that the crust had changed its distribution. So I like to sort of say that we can kind of imagine doing something very similar to this. So a black hole, let me go back one. A black hole has an infinite tower of multiple moments, but by the no-hair theorems of general relativity, it's determined only by its mass and its spin. And you can think of the mass and the spin as essentially moment 0 and moment 1. So if you're able to separately measure many entries on the left-hand side, you can check whether the constraint is satisfied on the right-hand side. What an amazingly pure test in the nature of gravity this could actually be. Now, that's a great sentiment. Then the issue becomes, how do I actually turn that into a measurement that I can do? Well, a lot of what goes into our measurements is understanding how radiation that are generated from these orbits back reacts on the system. And this led me to another complication as I began working on this problem. So this radiation has a flux to infinity, carrying energy and angular momentum away from the system. But there's also a flux down the horizon, which carries energy and angular momentum into the black hole. Interestingly, this down horizon flux can be reinterpreted, not so much as radiation flowing into the black hole, but as a tidal field changing the geometry of the event horizon. A useful way to think about this is that gravitational waves are nothing more than propagating tides. Okay, so we can think of the event horizon, it's either sort of in the infinite future from the standpoint of a distant observer who never sees anything actually cross over it. And so radiation falling into it is just constantly heading towards that event horizon. Or from the standpoint of that which is falling into it, it's a surface, it's a particular location in space-time. And those two ways of interpreting it allow us to recast radiation flowing into the black hole as a tidal field that changes the geometry of the event horizon. So here is an example, a little animation a student of mine made as part of his thesis work, God, almost 10 years ago, 9 years ago, showing what the geometry of an event horizon looks like due to the applied tide of an orbiting body. So to think about what's going on here, you're going to see a green sort of lozenge. That is that's the geometry of a Kerr black hole. Okay, so what I've done is I've taken this thing and I've kind of found a Euclidean surface that has the same geometry. It's like a soap bubble that has the same geometry that a black hole would have. And then what I'm doing is saying, how does that soap bubble's shape change as this guy's tide varies on it? So the orbiting body is in an eccentric orbit and has very little effect when it's far away. You can see it rotating. That's why we drew those little axis markers. There it comes, coming back in now. And as it gets closer, it raises the tide and changes its shape. That change of shape actually back reacts on the orbit and changes the evolution of these systems. Some of the work we've done has suggested we should be able to measure this. What's kind of cool is that when you look at this, the behavior is remarkably similar to what you see when you look at the tidal response of a fluid body. Okay, the same physics governs why the moon always has the same face towards us. Okay, the moon has a little bulge that was raised on it. 1 billion years ago was probably spinning, but because it had a little bit of a bulge, the Earth's tide back reacted on that bulge, took energy away from it. That actually changed its orbit, took energy, angular momentum out of the moon until it got to the point now where it's locked to us, tidally locked. So what's kind of interesting is that the equations that govern tides and fluids, one way to think about what's going on is it's related to how entropy is generated due to the fluid lines rubbing against one another.
Does
Yeah.
this go beyond this usual like membrane?
Not at all. In fact, that's my next slide. You're a step ahead of me, dude. So a very similar thing happens with black holes, which is that you have a two-dimensional surface, which you can regard as being generated by the light rays that live in that horizon, the generators. And there is a generation of entropy in the horizon. In other words, making their the area change. The constant proportionality that relates how the tide changes the generators is related to the rate of generation of entropy by a constant that happens to have the dimensions of viscosity. So you can think of the black hole as being a very viscous two-dimensional fluid. And of course, it being a black hole, when you actually look at it, it ends up being nothing but C's and G's that are coming into this. But nonetheless, this has the dimensions of shear viscosity in 2 dimensions. Yeah.
Good question. So does this mean that the vorticity of the generators on J is still rigidly rotating at the same speed
Yes.
as before?
Well, it secularly evolves. Okay, so there is a secular change to this thing because when this back reacts on it. So when you actually go through some of the details of what are these papers by Hartle and some of the others that are cited here, and there's something you can go back to Hartle and Hawking. You use the fact that you are sort of adiabatically evolving through a sequence of black hole orbits. You use that constraint to determine how the mass and the angular momentum are changing. Okay, and the radiation tells you how much of this is going into mass, how much is going into angular momentum. And so there is a secular evolution of these things. But that ends up being something that back reacts on the orbit and becomes an observable that we can try to back out. So all of these things that I've been talking about, these are all just vacuum two-body solutions. Okay, I've been very excited about this for years, but I'm starting to realize as I look at what kind of data that we're now seeing, that these really constitute a platonic ideal of a binary system. This is the way most general relativity theorists think of binary black holes. The entire universe is binary member number 1, binary number 2, and then your gravitational wave detector and you sitting there looking at the data coming out. And as Shakespeare taught us long ago, there are more things in binary spacetime that are dreamt of in your philosophy. Okay, you have to get the general relativity edition, but it's in there. So what if you have a third body? Indeed, for many of these LISA systems, we expect these binaries to be created in regions that are pretty dense with stars. So a number of years ago, some colleagues of mine wrote a paper where they said, well, what would happen if we had one of these extreme mass ratio systems, and about 0.1 parsecs away from it, there was a 10 to the 7 solar mass black hole. Well, what you find is that the third body breaks the space-time acting symmetry. tidal fields squeeze the binary, and what they end up doing is exerting a force relative to the background orbits. This force, the tidal force to these things, it's almost sort of nugatory for most of the time. Its effects tend to average out, except near places where the radial and the axial motions are in a low order resonance. And then what happens is that the mathematical operation that averages out most of these things fail to average at these points. So what you find is that when you're passing through these moments where things are in a low order resonance, the system gets kicked. And the orbit precesses and it changes its geometry. Now I looked at that and thought, well, how many Emrys are going to have a 10⁷ solar mass black hole 0.1 parsecs away? You know, there might be a handful, and they'll be really interesting. But then I realized that the tide from a 10⁷ solar mass body at 0.1 parsecs is identical to the tide from a 10 solar mass binary at about a light day. And guess what? We have about a dozen or two stars just in our galactic center alone that meet that standard. So we've come to realize that we absolutely are going to need to model the impact of third bodies as one example on these things.
So Scott, there is the Newtonian effect called the quasi-Lidov.
Yeah,
This
absolutely.
is really the same thing, but GR
This is, quasi emerges as a limit from this.
as a limit from this. Okay.
Yeah, there's aspects to it that are a little bit different, but quasi certainly emerges from this, yes.
What is the code? I don't know.
So quasi is, imagine you have a hierarchical binary, okay? So I've got two bodies that are orbiting each other like this, okay? And it's got a particular eccentricity associated with it. And Priya is holding a massive beach ball over her head that's itself exerting a large gravitational interaction. So basically, due to a very similar kind of physics here, there's an interaction with that distance perturber. And what that does is the tidal effect of the beach ball that Priya is holding back reacts on the system. It does so in such a way that it's going to conserve angular momentum, but it'll cause a secular evolution in this body's characteristics. And so one of the things that comes out of this is that the eccentricity gets pumped up, changing the orientation in such a way that the angular momentum is conserved.
It's the tidal force from that.
Yeah. So this is very, very similar. And I would say that the thing which sort of woke us up about this was realizing that for these long-lived sources, and I think that's one of the main issues, that these are in much longer-lived sources, and they're in very crowded astrophysical environments. This is not just a simple two-body problem. Okay, so we don't have a spherical cow, we have a cow. Another one, I'll sort of wrap up in a few minutes with this, is the discovery over the past couple of years of these quasi-periodic eruptions. So there have been a variety of systems that have been found, often following, so this is adapted, by the way. So Aaron Carr's graduate student, Johin Chakraborty, is working on things related to this, and I'm on his committee, and he gave me his slides. These exhibit strikingly regular eruptive flares. So this is an example, one of the first ones that sort of started this discussion. This was an event that started out as a simple tidal disruption event, 2019. And at first, it showed all the normal characteristics of what happens when a star is disrupted by a black hole. You know, it was very exciting, but it didn't seem all that unusual. But then, starting around 2022, people noticed that it was flashing in X-rays every 9 hours. So the hypothesis is that what's going on here is that there's an orbiting compact body that is interacting with the disk of material. In this particular event, the idea was that the star that was disrupted was an evolved giant. So it had something like a degenerate core, basically a white dwarf at its core. Everything that was not in the degenerate part of the star got disrupted, formed an accretion disk, and now you have this white dwarf core that is orbiting and striking this disk. So Itai Lineal and Brian Mesker have a very nice analysis of what this might be, what be going on with this. There's another example. So this is a big part of Johin's PhD thesis, is a particular source that's been monitored for about 3.5 years using NICER. It also is showing regular eruption events. But what's interesting is that if you make the sort of the most obvious timing models, you find that there are residuals that are sinusoidal from that thing. And one of the interpretations of this is that what you're seeing is that this is orbiting a rotating black hole, and there is a sort of beat between the orbital frequency associated with precession of the orbit and precession of the accretion disk.
So in that TDE,
The one talking right here?
Well,
the previous one?
Previous one, the white dwarf core didn't get sucked into the black
That's
hole.
right, that's right. So it was, if it was an evolved giant, you would expect there to be a lot of mass that is not as tightly bound. And so perhaps part of the star was sort of close enough to the Hill radius that it was pulled off and it formed
I
this
see.
disk. But the core was sufficiently bound that it remains together.
And that's what's going through the debris disk.
That's the
or-
hypothesis. That's the hypothesis, yeah. And these are all things that ultimately is going to need to be tested. So yeah, this is another one that, it's, you make your models and you test them, and, Joheen loves this interpretation, but he's ready to throw it away. If someone comes up with, one of the things that we should see with some of these, if these are in fact orbiting bodies, at some point, we should see the frequencies evolving in a way that's consistent with some kind of back reaction. And on that note, there is another one. So this is one that another student at MIT has done a lot of work looking at. It was a tidal disruption in March of 2018. It started showing these quasi-periodic oscillations in 2022. Initially, it looked like something that was consistent with motion near the last stable orbit, circular motion near the last stable orbit of a black hole that had the mass that had been determined for this system. But over time, that frequency changed. But it's been changing in a way that is completely at odds with what gravitational wave emission should be. Okay, so depending on what the mass of the secondary is, you would expect gravitational wave emission to follow one of these colored curves. What is actually seen are these black dots. It's so coherent that it really smells like something orbiting, but it is not evolving like a GR emitter. One hypothesis is that this is again a white dwarf, which may be generating gravitational waves, but it's also losing a little bit of mass. So some of that mass may be being dumped onto the black hole. Per the comment you made to me earlier, you lose mass, you don't lose as much angular momentum, it changes its orbit. So this situation, so this is what's been happening in the past couple of years. And one thing that's worth mentioning is that if
wouldn't you need a spectacular rate of mass loss? This looks pretty dramatic, right?
it doesn't have to be that much, but it is pushing things. Yeah,
It is pushing
it is pushing things. Notice it is starting to level off here. So the hypothesis was that although it's moving to higher frequency, so maybe something is going to happen here. So keep an eye on this. Again, everyone is perfectly willing to throw these models out. And one thing to be said is that if this is a binary and it's still around, it's right in Lisa's band. So I'm going to wrap it up here. The thing which I kind of, I go through some of these examples, because as I think about the future of this field, it's really determined by what's been happening in the present. And I started in this field as a student of Kip Thorne's. I began in 1993, and we were all GR theorists, and we were all looking at this and saying, look at all the cool gravity we're going to do with this. And I haven't seen any evidence yet that there's anything beyond Einstein's general relativity. It's almost like the field equations. We should just think of them as like Maxwell's equations. They're the tool that we use to get to the really cool physics. A lot of the really cool physics is going to be in the astronomy and the astrophysics that is governing all these different kinds of sources. So as our measurements go deeper, I think we're going to need to start putting a lot of detailed physics into these models, really think about how to do these things in a self-consistent way. And it's going to be hard, okay? 'Cause these are, as I don't need to tell quite a few of the people in this room, you need to put in, astrophysics brings in a little bit of everything. I'm actually teaching Astro 1 to grad students right now, and there are parts of this class where I am honestly one lecture ahead of the students, because it's like, oh God, radiation transfer, I never use that. How does this work? And I think all of this, that's one reason why we all collaborate, is that these are hard and you need everyone's expertise. I will say though, that I am personally, so as I say, it's crucial to keep an open mind, we need to bring in other data channels. We don't want to be fooled by things that look like new physics but aren't. And I think we're going to see a lot of those. And as I was starting to say, I am lucky. I have a family member who has an innate ability to model some of these sources. And so I'm getting her involved in things, and I'll exhort everyone else. Get your students started while they're all right, thank you. By the way, she's now 13 and she's a little ticked off. So I wanted to make sure. She'll be amused in 5 years, but not at the moment. So.
So the last two examples you showed, Chakrabarti and Masterson,
Yeah.
beautiful. I mean, those are really interesting, puzzling things.
Yep.
Both are very much astrophysics, right?
Yep.
it's mass transfer or interaction with a disk
That's
or,
right.
you know, whatever, Pardee Peterson, this and that and all that. So I agree with you, that makes astrophysics, and then, that's a very, very grungy
Yeah.
field. But I was just curious, do you consider this one of your known unknowns, or is it an
Yeah, I
unknown
would
unknown?
put this now, so this was, look, an unknown unknown becomes a known unknown. And so this, to me, this is an interesting sort of story here, right? When I've been giving talks on things related to what Lisa's gonna learn from measuring emeries for
Yeah.
15 years, right? And some people would often say, well, what about, one that occurs, is associated with accretion? Are you worried
Mhm.
about that? And I would say, that would be cool if it happened, but I don't expect it to happen. And I usually made an argument about the fact that the number of active galaxies is a small fraction of the numbers that are non-active. And I look at Sagittarius star and sort of say, look, there's already a lot of stars down there. There's very likely a lot of compact objects. We're going to be measuring these things out to a redshift of about 1 or 2. There's going to be a lot of them. The ones where that's happening are going to be complicated ones that we don't really expect will dominate the data. Now I'm just not sure, right? The fact that these are all relatively close by objects and we're seeing a bunch of them, they're all, I would say many of them probably it's something related to a white, if these are binaries, a lot of them are probably white dwarfs. Although there is another source that appears as it has been interpreted as it was a TE in which they saw sort of quasi-periodic eruptions happening almost instantly. And the hypothesis was that it was an emery with a black hole that a star then disrupted it. And now that black hole is interrupting with an accretion disk that wasn't there before. I couldn't find the papers on that one in the rush to get this talk together. So, I like I say, I take this was totally unknown. I mean, 7 years ago, I had what in retrospect was a pretty wimpy answer for why we didn't need to worry about it. It's probably totally wrong, right? And so I just converted it. Now it's known, what's unknown is the right way to model these things. How often do they occur? What is the nature of that secondary? Is it going to be one, what's kind of interesting about some of these is this may put selection effects on the kind of sources we are looking at. Are these predominantly modest eccentricity? Are these, should we be focusing on sources where we have sort of an X-ray trigger that we can follow up on? One of the things which is if these models hold up, monitoring this both in something like NICER or AXIS and LISA, it's an incredible standard siren. It's an incredible probe of the nature of accretion. So, there could be a lot of science out of that from the known unknowns.
But I was actually drawing the opposite lesson. Because these two examples are examples where we are seeing electromagnetic radiation. Therefore, there's other stuff there.
Right.
Making it dirty.
Right.
But maybe for the gravity, you want the guys that don't produce the electromagnetic radiation because they may be clean and pristine.
Yeah.
And we still don't know what's the ratio. Right?
That's
the original excuse you gave is still a good one.
It's still a good one.
Yeah.
But I feel a lot less comfortable giving it.
I'll buy it.
Yeah. I mean, I fool me once, shame on you. Fool me, that kind of a thing. So I kind of feel like at this point, I can't pull that nonsense anymore. And so I think
we're all good with dirty astrophysics, actually.
Yeah, it's great, but not for testing multiples of GR.
Yeah. So I mean, if this kind of comes in, I mean, one thing, if I come back to this sort of model of how we do the self-worth calculations, there are very elegant calculations based on just the two-body problem. Here we go. That tell us that we need to be able to sort of solve these equations to second order. We need to be able to include all these things in order to kind of get the phase right to the particular level that we would need in order that in a 1 or 2 year observation, our models remain phase locked with the data. Well, if we have, for some fraction of them, a bunch of sort of muck in there that is completely pushing us away from this system, sort of says, well, do you really need to be worrying about some of this stuff? Should we not be making perhaps cruder but more robust models that can be used even if there are some known unknowns that are in there kind of poisoning what you're looking at? And sort of in the theme of where do we go from here? I think a lot of people need to change their thinking about the way that modeling is approached for these things.
But even with this self-worth, we don't even have like fully evolved waveforms for like spinning, right? Like there's this like hole in like even if in this very
at a idealized setting, I think we are still not up to the task, right?
I think we have first order,
Yeah,
dissipation only. The impact of spin is understood how to do the calculation.
as a snapshot, right, of like.
Actually, there have been recent work, we now know how to do back reaction associated with those as well. So, but literally a paper that came out about a month and a half ago. So, you know, I'm cautiously optimistic we sort of have that under control. But there's a lot of, someone needs to turn a lot of cranks, right? So at the end of the day, there's a fair amount of almost engineering level labor that needs to be done. You know, and you know, that's actually what I'm spending a fair amount of my own personal research time on these days, is things related to that kind of engineering level labor. But you know, you're not wrong, but I'm a little more optimistic than you sort of initially phrased it. But I would say that, you know, really modeling things kind of at the next order, nailing these things down, making a two-body solution that's accurate to a fraction of a radian on a 2-year thing. I would love for there to be a couple of sources where that's relevant. I don't know whether that's going to be the case, and I think that's become a much bigger known unknown than I would have guessed 8 years ago.
You mentioned this really interesting effect of tidal heating.
Yeah.
And you discussed this situation where you have like gravitational wave inflow down
Yeah.
the horizon. Is that what you were referring to when you said tidal heating? Because you also mentioned there's an exchange between.
Yeah. So that's related to, let me go back to the slides that talk about this a little bit. That's related to the fact that there's this duality between this. So there's additional slides I could have shown here, but the interest of time I had to sacrifice a few things. So there's, when I actually do these kind of back reaction calculations, you know, I solve the equations that govern a perturbed black hole. There's a solution that is regular very, very far away, and that tells me about radiation that flows to infinity. There's another solution that's regular on the event horizon. I sort of use both of them. I can use them to construct a Green's function, and it gives me the complete solution. And so the one that's regular on the horizon tells me about the amount of mass and momentum that's absorbed by the black hole. Both of them back react on the system, okay? And so there's a level of this calculation where you can sort of ignore the fact that this duality exists and just say, I just want to know how much energy and momentum goes to infinity, how much goes into the black hole. I'm going to oppose global conservation and do back reaction, and that's great. But it turns out that you can also sort of regard what's going on with that as this sort of picture that the radiation that's going into the event horizon is governing the dynamics of what the event horizon is doing. And what I didn't have time to show is how precisely we can measure the effect of this thing. And so that if the black hole has a modest spin and the orbit is not too far inclined from sort of the equatorial plane, the effect of either down horizon flux or orbital, the tidal distortion of the horizon, it changes the phasing of the orbit by thousands to tens of thousands of radians. It is a very significant effect, basically because these are very long-lived signals. Kind of comes back to my initial theme, that there's physics that we only see when you have lots and lots of cycles that sort of builds up and accumulates. And this, I think, is an interesting example of that. And one of the things, so I'm collaborating right now with some people who were students of Abba Ashtakars, who really have this, they have this language of isolated horizons. It gives them really elegant tools for understanding these things. And we're sort of noting that this is another example of kind of like a precision test of the foundation of general relativity that can be done. You know, there's, when you have the sort of shape change like this, you can characterize this as a form of multiple shape to the horizon. And the boundary condition that general relativity imposes strictly sets what that must be. If we can measure that precisely, you know, that's at least a sanity check of things here. Is it going to be a road to sort of a deeper understanding of gravity? At the very least, it's a precision check of the foundations, which I think is, well, it's a foundation seminar. So there you go.
Perfect.
The person in the back, you
yeah.
say.
I was wanting to say that you've shown how tidal effect would distort the shape of the horizon.
Yeah.
Would you expect it to affect the multiple moment measurements?
No, because those multiple moments, so there's two issues that are going on here. It's a great question. The multipoles are defined in the unperturbed spacetime, so they are kind of a dominant effect. The multipoles of the spacetime itself, the ones that sort of govern the curve solution, they are defined in the background spacetime. The ones which I'm showing you here, I've actually exaggerated them for the sake of making them visible on this plot. They are a correction to those multiple moments that are suppressed by a factor of the mass ratio. Okay, and so they separate in the time domain when you actually do that analysis. So one of them sort of accumulates over long times. These, they also accumulate, but they're sort of accumulating in a different way because they're suppressed by the mass ratio and they're time varying. The other ones are not time varying. That's one of the main issues. Yeah.
Okay, I have.
Hell,
Is this on this, right?
sort of related to this, yeah. Shall
I
I?
don't know.
Yeah, it's just reminded of something that's confusing me. So you're talking about this, very, very physical language, distortion by the tidal forces,
Yeah.
dissipation and all that stuff. This is, all the whole discussion of love numbers for neutron stars is about these kinds of effects.
Absolutely.
And then I've heard talks in this room where people say black holes have zero love numbers.
That's right.
So what's going on?
Okay, so what's going on? And by the way, I'm delighted you asked that question because this allows me to be. I have the gray hair and I'm in my mid-50s, so I'm finally aging into the personality I've always wanted to have, which is a cranky old man. The language around this, the language around this is confusing. There are actually multiple notions of love numbers that are coming into play. So the one that has zero love number for a black hole.
Yeah.
It's related to the fact that when you apply a tide to the space-time, you don't. What you are changing here is the response of the geometry of the horizon, but you are not changing what the gravitational potentials of the black hole actually are. Okay, that is what that love number actually refers to.
Yes.
Okay, and so the person who I'm working with on this is Badri Krishnan. He was a student of Abhay Ashtakar's, sort of splits his time between things related to the physics of event horizons and LIGO data analysis. And this drives him crazy as well. And so we've been calling this surficial love numbers. Okay, so this is simply, we're looking at the geometry of this surface. And what it really is it's a representation of what the sort of shape of the event horizon would look like according to a certain system of preferred observers, which I think nicely communicates what's going on with this. But in another sense, this thing is actually remaining spherical, right? But in the coordinates I've used to present this to sort of govern what's happening with this thing, I've shown this distortion. It is definitely confusing, but I will defend the way that I've shown it here because these things do in fact, because there's a one-to-one mapping between the geometry of these things and this sort of loss of angular momentum from the orbit, there's a strong connection between that picture and what the orbit is doing. And it has an exact correspondence to sort of Newtonian tidal coupling. So I think moving away from that kind of language would be crazy. I mean, it is wonderfully illustrative. But you then need to talk about what's happening with this other family of love numbers. And I think somebody needs to actually make this language clear and precise. And it hasn't quite happened yet.
The vanishing is only of the starting.
And stationary.
Shamelessly plug my talk in half an hour, which will be about that.
Okay, good.
Very good. Very good. I have to unfortunately get ready to teach.
These two notions of love number.
I will focus on the ones on the far zone, but the dynamical ones which are not zero. Yeah.
Excellent, excellent. Yeah, so I sadly will not be able to save that because I have to teach the equations of stellar structure in about an hour and a half. So that means I need to go back to my office and relearn the equation of stellar structure.
Okay, let's take Chef's question and then we'll wrap up there.
So there's a lot of tools here to look at the data. And I'm just wondering if, in spite of the astrophysics that can confound tests of GR, that there are some like corner cases. There are some weird cases for non-GR theories that could be constrained by what we have now. Or are there black hole mimickers like boson stars or something else that could, in some sense, be ruled out because the fits to those spacetimes would be sufficiently different from astrophysics.
That was partly what motivated this sort of kind of an analysis, because this idea that the space-time, I can describe any axisymmetric space-time using a family of multiple moments, okay? But Kerr, because of the no-hair theorems, which tells you it can only depend on mass and spin, in the mathematical structure of these things, you have this sort of beautiful association where if I measure the first two moments, I know all the rest of them. Any other object that kind of comes along will end up changing that. And so there's an example that in a particular, Nico Yunus has probably written about 35
But
papers
you
on
did
this.
bumpy black holes.
Well, that was what bumpy
right?
black holes was motivated by originally for doing this kind of a thing. And, I originally formulated this as trying to be theory agnostic, model agnostic. So imagine you have a space-time that the multiple structure looks like this, plus deltas, and the delta is due to whatever schmutz in your model, be it GR, a third body that you mismodeled, whatever, try to come up with a way to characterize that. And Nico Yunus has written some papers where he sort of thought about theories of gravity, blanking on the names of some of them, but there are ones where it looks like Kerr up until a certain multiple moment, and then there's like a tweak to that kind of a structure, and that's sort of a straw man that we could imagine constructing something in, and then using that as a way to test some of the structures of some of these things. So, corners like that are very, very interesting. I mean, part of this talk, I think, I've phrased things a little bit in terms of parables. And you can kind of think of this entire talk as the parable of a GR theorist learning how astronomy works. Right? So, part of this is me coming to realize just how messy some of these things are really going to be, and how there ain't no spherical cows.
And then you have to teach astronomy 1.
Exactly.
Indeed.
It's a fabulous talk.
All right,
Yeah.
well, thank you.
Thank you very much for bringing